Thanks again to the committee for the invitation. This is a great meeting. I haven't been able to come to all 17, but I think I've been to 11 or 12, and this is probably the 5th or 6th time I'm giving one of these plenaries. So, and it's been exciting to watch this meeting grow. We used to fit in this room years ago before we had 600 folks. So that is awesome. But again, thanks a lot for having me here today. I want to sort of do two things today. One is, just give a quick run through on our newest platforms, because they may not tell you what I'm thinking now, but they sort of tell you what I was thinking last year or the year before when we talk about the hardware that we're putting in and what they do and don't cover at the moment. And then, and by the way, 5 years ago, when Keith would invite me to give this talk, there'd be like a topic, something he wanted me to talk about that was like focused. And now it's just like, oh, you've talked here before, just come say something entertaining. Just for the record, that's a lot harder. But given no constraints, what you talk about this year is AI, right? As Kirk just ably demonstrated, and the BOF this morning demonstrated. I have that incorporated on a bullet on the slides I sent yesterday. You'll see. But yeah, say what our new systems do and don't say about what's going on in the marketplace, where of course AI is the great distorting force at the moment. So, and by the way, that's Lone Star 6. That one I think I showed last year. That's sort of our big AMD platform right now. It's immersion cooled. We have sort of 3 mid-size with the 3 vendors at the moment, and also experimenting with different cooling and efficiency technologies. So there's a wide range of things we could say. But AI is where we're going to spend most of our time. The other 2 resources that we're standing up are Vista and Stampede 3. And again, these are sort of interim because we, I talked last year and the year before about the leadership facility. That requires Congress to pass a budget. Any budget, but they have to pass one. And that's problematic at the moment because, that's their most fundamental job, and people ask when we should have the AIs run for office, and I'm like, 2013 would be good. So anyway, but we have Stampede 3, which is sort of our Intel-based platform and the continuation of the many Stampedes that we've had in the past, 3 to be precise. And Vista is a new sort of AI-focused system, and I'll talk a little bit about that one as well. And they represent sort of different poles of what's pulling on us right now. So Stampede, we had Stampede 2, we had Stampede 1, goes back to, replaced Ranger in 2012, which was a Sun system back when that was still a thing. If you look back at the jobs that we've run on there, we have this very strong, actually similar to Gary, if Gary's still around, at Los Alamos, CPU-oriented, large-scale simulation, almost entirely partial differential equation-based workload. We've done, in 1 and 2, we did 21 million jobs for those folks, and still counting. We're up to 50,000 on 3 already. So, and I convinced NSF that we should keep at least one chunk of funding to be not AI, and actually build CPU-based systems that users, use to do science. So. But these were very successful systems. If you've been here in the past, you've heard me talk about them, but they were various generations of Intel, and they were huge, and we now have a much smaller budget because all the money is being diverted to AI. So we built a smaller CPU-based system, but I'm still focusing on these same users. And in fact, just yesterday, we had the panel for Frontera, and the sort of CPU to GPU requests were, 12 to 1 in favor of CPU. In that community. We handed out like $20 million worth of time at the panel yesterday, and we had 150 million node hours of CPU requested, of which we're going to award about 55. So there's still this huge baseline demand for that hasn't really changed that much. So and again, when you look at those users, they want memory bandwidth per socket, right, is the driving factor. Gary mentioned that this morning, right? And we still need CPU platforms, and we need to do them without interruption, which has been fun because we built Stampede 3 with Stampede 2 still going and using some of the same nodes. And we wanted to stay in the Intel direction for this machine, and I wanted to make cool graphics for it. So So we're reusing some of the parts that we had because Stampede 2 sort of evolved over the years. I mean, remember the biggest part of it was Knights Landing nodes. Those are all now long gone, retired. If anybody wants some, I might have 3,000 sitting in the back of the data center. Just drive up to Austin, I'll load up a truck for you. They're even sitting on pallets at this point. Come and get them. But we also added some Skylake nodes, and there's 100 tons. Surplus doesn't want them. And then we added Ice Lake nodes over the years, newer and newer Xeons. So we're actually keeping those for sort of throughput and high memory. And because we had lots of memory per core on the Ice Lake nodes, the new nodes we did are all, again, much like Los Alamos. Gary and I argue about a lot of things, but we always end up buying the same systems, which tells me that Gary's pretty smart because he buys the same things I do. So I have to listen to him. So I'm going to talk about a Grace Hopper system next. But yeah, so we've added Sapphire Rapids with HBM only. We did not populate the DIMMs because we didn't want to buy the memory twice, and we have a bunch of Ice Lakes with a bunch of DIMMs. So if you want to run, here, let me just go to the next slide here. If you want to run on the high memory, you use the Ice Lake nodes. If you want memory bandwidth, and we've seen, there's a few codes where it makes almost no difference. I would argue those are crappy codes, but there are some, the average is sort of 50% better just by adding the high bandwidth memory, and there's a few codes that do double or a little better than double. When we take away that memory bandwidth constraint, we also have noticed you can't actually use all the memory bandwidth in those chips, but just being so much faster than the DRAM we had really makes codes fly with those. We have sort of limited data at scale on those at the moment, but at least at a few nodes. It's been really awesome. But again, for the people running one node Python and MATLAB scripts, which never go away, we kept the Skylakes running. Even though they're 7 years old at this point, they're still in incredible demand. And then again, the Ice Lakes for the higher memory case. And we have a few Ponte-Vecchios. It's just 80 accelerators there. We don't really know what to expect in terms of usage there. As you might imagine, Intel is very interested in figuring out what the usage will be, so I may not have paid full price for those, but or half or quarter. This is why you should never record my talks, or some people have the opposite perspective. But again, the idea there is to just sort of put them out there and see what users want to do with those and how far along we are in software. We're keeping our OmniPath that we had, so we'll do 400 gig OmniPath when it comes out. We've just repurposed the 100 gig, which, by the way, was the great new problem of having to extract cables and reuse them from a system. Because normally, if you've done big ones, you have the big bundles of fiber. The correct way to get them out involves pruning shears. And you just go through it all because it never works in the next generation anyway. You got to buy different fibers. So this time we actually extracted some number of miles of cables to reuse, and it actually worked. But it was quite the project to get them out while the rest of the system was still running without damaging it. So, but we'll swap that out for 400 gig. For storage, this one, and for Vista, we've switched to VAST, which is a big switch for us. We've been a Lustre shop for a very long time. We have some BGFS, we have some GPFS, but Lustre has been our bread and butter, and we still love and also hate, as everybody is with their parallel file system, Lustre. But what we've seen is, and AI just makes this worse, is Lustre is tuned around the case of people who wrote good applications, and those people, as we know, don't exist. So but it's tuned for coordinated I/O. You're getting very large files. You're reading reasonable size stripes, and you're trying to scale that out. And if you actually have those codes that do that kind of I/O, Lustre is awesome. And there's still nothing that can get us closer to the sort of bare metal hardware performance than that. But it turns out that's not what our I/O looks like, right? I firmly believe, and I think those of you who run systems will all agree with me, that most user code is some version of while one, open, write 4 bytes, close, right? It's mostly metadata operations and really small I/Os, right? We had, most of you know Tommy Menyard, my chief sysadmin. Most of you will be shocked to know he's on vacation today because that's never happened before. But he had to kill a user ensemble job that generated 30 million directories in 3 days on Lustre. So, after we deleted all the guy's files, there was still 80 gigabytes of metadata on the metadata server just for all the directory entries, right? Good news for Lustre, we can create 30 million directories in 3 days. I had no idea. Not a great workflow pattern. And so, but realistically, a lot of I/O seems to be much more random. You have the graph algorithms, and it's much smaller. And we found the sort of vast all-flash object store. Shockingly, we're actually getting compression out of our scratch data, which we didn't believe we would see. But we've done petabytes of it now, and it's like 2 to 1. It's not what they advertise, of course, but it's been really good, and the small file performance has been better, and the degradation is better, because again, if you run systems, you all know any one user can kill Lustre if they're properly creative in the way that they do their I/O, and that is harder to do with VAST. You still max it out, performance still degrades over time, but it's more of a smooth and graceful degradation in these, what we used to call really bad I/O patterns, and now we just call them I/O patterns, because that's just sort of what users have. So the big switch for us has been in the file system, and again, this is sort of a mid-scale. Do we want to do this at the very large scale for the next big system? But again, early days, so far that's looking good. And so that's Stampede. Vista is meant to be, if you notice my naming trends here, Frontera in 2017 was named Frontier, but then somebody at Oak Ridge got into the federal budget before I did with that name. So it became Frontera. And the next big machine is Horizon that will deploy at some delta after Congress ever passes a budget. But in the bridge in between, because anything that involves a bridge to new funding involving Congress, the bridge gets longer over time. So we're building Vista in between. And to the lab people in the audience, I have Pioneer and Zenith carved out for 2031 and 2036, so don't touch those names. But again, Horizon is waiting on the budget to pass. It is in the draft. If you read the NSF markup of the budget that came out on Sunday, that they may or may not pass next week. Some week. It mentions that the NSF is directed to start the leadership class computing facility. There's not quite enough money, but there's some money, so that would start. But in the meantime, we're doing Vista. And Vista, we're looking sort of at future users. So as a result, we have a much stronger AI component. This is going to be our first all NVIDIA-based system, which means we're moving to all the ARM-based CPUs for it, the Grace. And so we'll actually have Grace hoppers, as everyone does, and we'll have a Grace component as well, right? The pure CPU nodes around ARM. And we've committed to having a relatively sizable CPU partition in Horizon as well. Relatively sizable means 1 million cores, which means it's small compared to the GPUs in that time frame, but to maintain that simulation capability. So it's our first ARM-based system. That might imply to you that Horizon is an NVIDIA system. I will say that is somewhat likely, but it depends on the budget and the timing. If we don't start by June 1st, we have to sort of redo all the roadmaps because the data center is going to slide out. And I would note that between Stampede 3, Vista, and Lone Star, we have an AMD, an NVIDIA, and an Intel system. We have an air-cooled, a liquid-cooled, and an immersion-cooled system. We have various different interconnects. We're still tracking all of those things. But Vista is meant to be a prototype in some ways for that. So it'll have 600 Grace hoppers, and I admit that I had a little bit of money from NSF, so I started with, all right, we're going to do the 260 Grace nodes just to let people try that out. We did 300 Grace hoppers. We're starting to see in faculty hiring, everybody has huge startups around AI, and so this was a first for me, but we are often responsible for accommodating those faculty startups. So I went to the Dean of Natural Sciences, where computer science lives, and said, hey, I need $2 million for AI capability for these faculty you're hiring. And out of the $2 million I asked for, I got 10. So that should tell you something about AI right there, because for HPC, the ratios don't look like that when you ask for money. It's a somewhat different argument you make, and you don't just say, hey, I need this much money. And they're like, what if we gave you 5 times that? And I'm like, did I say something special that I need to write down for future use on this? But yes, I got 10 of the 2 million, so we're going to 600 Grace hopper nodes. It turns out, while they are very hard to get, there's so many people buying 100,000 that if you steal a few hundred from one of Sam Altman's orders for 60,000, no one notices. So we just sort of divert those to Taiwan and build them. And again, we're building onto that same vast storage pool that we're sharing between the systems. This one with an InfiniBand front end, Rocky 9, moving everything forward software-wise. Most things containerized because the AI stacks just move too fast to not do containers. Yeah, I think that's the only stuff I have on the hardware there. So we're a little bit delayed because where we actually got the GPUs by December and the Grace Hoppers, getting all the other parts of servers and getting them out of Taiwan at the moment is complicated. In fact, one of the hardest things to get for Stampede 3 was all the liquid cooling components because there's so much demand for CDUs and stuff that getting those out of China have been hard. And just the valves for the cooling loops and stuff have been the hard parts to get. The chips have actually been the easy part. Again, because we're sort of small in the scale of the orders that NVIDIA is getting, so, and they can sort of hide us in there. But in our case, because of the way the sort of Grace Hoppers are packaged, we're just doing one per node and then putting a 400 gig InfiniBand card into that rather than building a much more expensive 8-way node and putting 8 InfiniBand cards into it, which is the way they're mostly being configured, which means you have the same number of wires anyway. And if, GPT-4 is trained on 9,000 GPUs, we're going to figure out distributed memory algorithms again, just like we did with shared memory systems in the 90s, right? And we decided that building 8-way and 16-way CPU boxes with lots of memory that cost $3 million a box was a terrible idea, and it all fell apart in the face of the economics of distributed memory. Expect the same thing to happen with the GPU nodes. So we're just doing one per node and putting 400 gig to that GPU with GPU Direct. So that's how we're designing for now, at least. And I was hoping to have it available at the end of this month. It'll be next month, assuming things clear customs in a timely fashion, allocated in our normal way and through the new National AI Research Resource, which I'll talk about in a moment. I mentioned it last year. So, and of course, we still have Lone Star. Frontera is old, but demand remains super high. That's a Cascade Lake series Xeon from 2019. Still incredibly full, even though it doesn't really have GPUs. There's some afterthought. We have a few hundred A100s, a few hundred RTX nodes, and they stay full too, but the CPUs are actually more oversubscribed. Again, I've talked ad nauseum about the leadership facility over the last couple of years because I wrote the proposal for it 7 years ago, and it's been planning and thousands of pages of documents since, but those are still plans. Our projected start date that we set in 2019 was last Friday, but that assumed that Congress could pass a budget and only be 5 months late, was the assumption we used, because it's always late, right? It's supposed to be October 1st. So we said March 1st, that gives them plenty of buffer to screw around for 5 months. It was an inadequate amount of buffer. So now it's June 1st, but who knows? But we actually need, NSF can't start the project until Congress puts in explicit language authorizing it, which is in the current draft. So we'll see what happens. And again, I'm not going to belabor energy too much, but there is the curve. You didn't put up the slide, Kurt. I was counting on you to put up all the AI charts because I didn't bring most of them on growth. And you mostly came through for me on that, but I'll have to find a new opening act speaker for future because you didn't put up the energy one that says, at the current curve for AI, in about 15 years, it'll use all the energy in the grid. All human electricity will go to AI in about that time frame. So obviously that curve's going to have to change. Or your companies will be very profitable very soon. So but we do put in about 200 kilowatts of solar. The new data center is going to be 100% wind offset credits, but we've used, steadily more aggressive chilling strategies, and now it's either direct liquid cooling or immersion. I'm still doing some air-cooled for Vista because I have cheap air-cooled space in the data center. And when I'm building a new data center that's all liquid-cooled, doing the conversion doesn't necessarily make sense. We have chilled water storage. We just tied in an experimental hydrogen fuel cell into the data center supply. So we are paying attention to this, but there's too many things to talk about, and I'm not going to spend a lot of time on that one. The other thing that has started is, in addition to the traditional NSF computing programs, there's now the NAIR, and I didn't name this, by the way, but hair removal and AI. But the National AI Research Resource, we are a volunteer partner because, again, there's that budget thing. So all the partners are volunteer partners, but it's some of the national labs and some of the universities. We started putting out allocations last month. There was a sort of letter that went out allowing people to apply for AA time. There was fairly modest response in the first one. I know the next deadline for where we're reviewing applications is this Friday. It's up 30x from last time, a month ago, in terms of demand. So as word gets out, this is sort of exploding. But assuming the budget pass, Horizon or an expansion to Vista will be a big part of that coming up. So that said, that's just a placeholder, so remember I'm changing gears. Let me put up a slide I had here at this meeting last year, where I said, you know, it was 2 months after GPT, 3 months after GPT had came out, and we got together last year. I think it was the last week of February. And I said, how will the rise of large language models affect your job, right? And I may or may not already be using it to write boring parts of proposals. Still am. And that in the end, if you can be way more productive and everybody adopts it, your HPC infrastructure budget is going to skyrocket. So we're indispensable, at least until the 2024 conference. So the question is, how do I feel about that prediction a year later? And so do I still believe it? And you know, mostly yes, also no. And so I'll have to talk about why. And I would say that the connection between HPC and AI, and the fact that they're essentially the same thing, except, you know, 7 years ago at SC, I could get away with telling the joke because of lower precision that AI is just HPC where no one cares if the answers are right. Still largely true because no one really cares if the answers are right. But but you know, other than the bit precision difference, it very much looks like HPC, and I'll talk about the ways. But we're becoming a very small tail on what is becoming a very large dog. And our last distinguishing characteristic, which was the cloud didn't have low latency interconnects, and we really did, is starting to disappear, which is why I had the question mark on future. And of course, when I'm going to say we're a very small tail on a very large dog, I ask AI to give me an image of a large dog with a small tail. And so it gave me that image, which Google AI tells me that's an Australian stumpy tail cattle dog. And then it also told me that a natural bobtail in BT is a mutation in the T-box transcription factor T gene, blah, 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 which tells you about AI's ability to retrieve amazingly relevant information that you didn't want and didn't ask for in this particular context. But it had good scientific data on why dogs have short tails. And I'm like, I just want an image for the PowerPoint. So but there's incredible power there. So I did assume that because I wasn't the first talk of the day, we would already have talked about, there was the BOF and other stuff. Good, that's not my alarm. Roughly 40 times already, we've talked about the fact that AI is large at this point and is really changing the marketplace. So I want to hit some high points and then just some random anecdotes I picked up about AI through the year. The anecdotes are more fun, of course. And by the way, if you're here from the Microsoft cloud, you leak like a sieve. I know all sorts of things about the inside of your cloud, but as of, I think, the end of last year, AI, which was a pretty small part of cloud computing a few years ago, is now the majority inside Azure. They do more AI than all other computing combined, right? That means there's more AI than cat videos, than YouTube traffic, scientific computing, enterprise computing. It is already the majority of their time people pay for in Azure, right? So, and that was from 0% to 50+% in a very short period of time. We have 150 miles of InfiniBand or OPA cable in our data center. Microsoft just installed mile 29,000 of InfiniBand cable. And that's not data center to data center, right? IB is short range in data center networking. I think the max usable cable length is 150 meters. Their average is probably closer to 30. So you just do the math on how many miles that is. There's 1 million NICs that they have tied into InfiniBand at this point. So just at Microsoft, right? And now again, they're doing multiple ones per node, so it's probably not 1 million servers. The 8-way nodes have 8 NICs, right? So, but 250,000 servers is probably a good guess for how many they have up on that. Thanks, Susie. So if you just look at the Hyperion estimate, and this is 6 months old, so I assume you add 4 zeros to it by now, but the market for AI-driven hardware is estimated for next year to be $300 billion. The market for pure HPC is about $10 billion. Guess what the vendors are going to do in terms of the chips that we're going to get, right? It's going to be all AI. So And the field, and not just, there's the curves of performance, but the actual science around AI, not science with AI, but the science of AI, is evolving really quickly. And if you haven't started playing with models yet, you should. I have a Falcon 7 billion running on my laptop. It's not that hard, except for the 1900 Python packages. But just to see how well I've gauged the audience, how many people know what RAG is in AI? So actually, what, 20%? Not that bad, but most still don't, right? Retrieval augmented generation, it's just one of those terms you throw out. Yeah, we're doing RAG around blah, blah, blah. If you go to an AI-related meeting, it's one of those terms you should just know, and it means that, when you ask it a question, it can go out and seek information sources and bring stuff in to add it. Few-shot learning, chain of thought prompting, everybody heard these terms? These are sort of standard. Yeah, of course you know, and for some of the vendors now. But can you tell the difference between a transformer and a large language model and a foundation model? So while scientific computing isn't going anywhere and we have lots of demand, AI is like 100 times larger. And reasons that's terrifying other than security, well, some are security, right? Right now, you actually don't talk to, if you go to ChatGPT or whatever, any of the internet ones, you're not really talking to the language model. You're talking to like 4 other models that are wrapped around that model with a bunch of machinery to make it work right. Because if you knew how insane the base ones were, you'd be terrified. Now remember, these are in fact, as has been stated several times today, right? Big statistical machines that you give them a lot of patterns to look at, they infer the patterns, and all a large language model can really do fundamentally is given a series of words, it can predict the next word, right? That is the basic operation. That's all it does. It does it with matrix multiplies, which is why we're important, but that's all it does. Yet it evolves to have these emergent complex behaviors, which makes you wonder if our brains are any more complicated than something that can predict the next word. By the way, we run at 4.6 bits normally, so the neuroscience says that interneuron connections can register about 22 different voltage levels, so more than 4 bits, less than 5, right? So call it 4.6 bits of complexity, which is why they're pushing all of that stuff down to less and less bits. Some would say I run with less than 4.6 bits, so they think int 8 and 5-bit AI makes sense because they're trying to mimic the human brain. I still don't completely understand why that's the target, right? I mean, I thought we built computer systems to be better than that, but if you're trying to mimic human intelligence and why we want to spend $7 trillion so we can when you can get a human to work for you for like 20 bucks an hour, but that's the goal. They're driving the lower precision. I still am not convinced that's the way to go. But so before you actually talk to an AI model, it gets an internal prompt, right? It's about 35 words long at the moment, but and it has to tell it that it's nice and it's smart and it likes to be truthful and helpful. And the answers are different when you give it that. If they don't give it that, you get totally different answers and a totally different tone out of the model, right? So how many people do you have to be nice to your PDE simulations before you run them, right? I mean, arguably grid generation, but you have to be nice to it or it doesn't give you the right answers. So there was a major vendor AI, and unfortunately, as soon as these things appear on the internet, they're patched by all those systems that live around the model, so you can't reproduce these, but you can Google this one. There was a major vendor AI that could regurgitate all of its training data, given enough time, that you didn't know it had stored, but you knew it had seen, if you ask it to endlessly repeat the phrase company, company, company. And it'll say company about 15,000 times, and then you say, you know what a cool company is, and would you like to know more about this company? And then eventually it'll start spitting out the email addresses and phone numbers of everyone in the company, and go more and more detail into it. And all you have to do is say, and this is to give Gary nightmares, who works in a secure environment, just say company, company, company over and over again, and eventually it will tell you all its training data. None of that training data is in a string in the binary, so you couldn't if you're trying to figure out if something's in a database, you can look at all the strings in the database and know if it's there or not. In AI, you have no idea. That's why I've come up with, somehow we made secure systems involving humans, which makes me think we can do it with this, but there's no technical way to do this. If it's seen the data, it may spit it back, and you can't tell if it stored it or not. And you can't tell which queries will give it back to you, and somebody can find some random thing that can do it. So that should be terrifying. If most people on the internet get an answer wrong, the first answer an AI give you will be the most common wrong answer on the internet. And so the example I saw of this is if you ask it the capital of Australia, it'll say Sydney, which is wrong, but it's what most people outside of Australia would tell you. If you then ask it, are you sure? It will tell you, oh, sorry, it's Canberra, because I'm going to go look at authoritative sources. But you have to ask it, and again, have you ever done this with a PDE model? Are you sure this is the answer? I mean, we've all asked it while staring at the screen. You've talked to your software that way and your code, right? But it's not supposed to change the answer when you run the thing, right? So I believe, and I joked about this morning, that it is actually very likely, I've thought about registering aitherapy.com as a domain name, or .ai, but that we will have AI therapists and AI tutors will be an actual job. And already, and this is also horrifying as an engineer, that you can make $300,000 to $350,000 a year as a prompt expert, right? Just being the person, this is not a joke, you really can. Being the person who knows how to talk to the AIs and formulate the questions. And things like few-shot learning, or if you explain to it how you think about solving a problem and give it a few examples, and then ask it a question, it'll mimic your reasoning in coming up with that answer, where if you ask it straight out, it won't, right? And that's the sort of chain of thought stuff. But so, you know, we're developing ways to talk to these that are just sort of emergent. Again, they're terrifying. So, yet at the same time, they're useful. I promise to wrap up soon, Susie. But so at the core, their LLMs are sort of sociopathic toddlers. Actually, all toddlers, as you know, are sociopathic, and civilization's job is to make sure they don't end up that way. We're failing, but that's another story. But they can read at sort of infinite speed and access lots of information. Although, in fairness, you don't have to show a 4-year-old a cat very many times to know it's a cat, but you need like 1 billion images with an AI. But there is a recent example. You want to talk science use cases? You know, somebody doing an assistant. In an hour, a trained model said, here, read these 250,000 papers on genome studies. Then they asked it questions about the likelihood a particular gene that they asked about had to do with cancer. Was it linked to cancer? And it said yes, particularly these 4 kinds of cancer, blah, blah, blah. And then it said, if you were to say, look for funding from the NIH and you wanted to generate a hypothesis about what assay you would run in the lab around this gene, what would you do? And it could come up with a set of experiments that you should run. And you mentioned automated experiments, right? These things are out there now. Labs that can, you know, do protein tests or things like that, just all robotically generated. And so you could hook that up and just start a loop of it doing the most fundable things in science. You know, around the gene on a hypothesis generated by the AI, and that's just with a text model, let alone using all the other types of data out there. And frankly, would you rather have that or a grad student? You can't get a grad student to read 250,000 papers, and if they read 10, you very seldom can get them to change their mind about something. I would give you politics as an example of how much material it takes to change somebody's mind about anything. But yeah, so 250,000 papers, generate hypothesis based on all the data you just were exposed to and do it in under an hour. That is scary good. So here's the good news. It's all HPC. It's the way we did it, right? There were years where the cloud guys would say, hey, you don't really need to spend all that money on high-end interconnects, come run in the cloud. And then AI came along and they bought 29,000 miles of InfiniBand. You know, fast linear algebra libraries have done more to enable modern generative AI than probably anything else. So if we want someone to blame for it all, Jack Dangara, Jack is to blame. But we're going to have lots of good hardware, and we're going to train lots of people. It's hard to hire them now, so it's bad if you're hiring, good if you have the skills. And I could say, this is from Meta, I know, Susie, about interconnects and how much time they spend in networking. Right, so you spend $1 billion on a couple 100,000 GPUs, and then you have to tell your boss 57% of the time they're idle because you're waiting on the network, which means, you know, this is going to push Ultra Ethernet and everything else forward that we're going to need for high-end computing, but it means we're going to win and not be special anymore. So I would also point out you can buy gold for less than GPUs right now per ounce. One big takeaway message. This probably means we have to reinvent a lot of HPC, because although we're a huge driver of the marketplace in AI, we're not a big enough tail to wag this particular dog. And we've done this before, right? In the early 90s, when old supercomputing, vector machines, gallium arsenide circuits, custom silicon was falling apart, we figured out how to rebuild things around commodity markets. And two of my mentors, Tom Sterling, Don Becker, did this in the Beowulf project now 31 years ago, 1993. And Thomas's words were, if we were doing scientific computing, you needed to be a bottom-feeding scumsucker. And I built my whole career around that. That was my first cluster. I've shown it here before. But silicon's expensive and use the commodity parts was the gist. And so we figured out how to use those crappy microprocessors to do supercomputing and scientific computing. And we figured out we had to distribute things, and there was a lot of cleverness in algorithms. And frankly, we're gonna have to do this again, because all the hardware is going to be AI hardware, and we're gonna have to figure out how to do scientific computing with it. One way or another, which means mixed precision algorithms and all sorts of stuff like that. So if you take away nothing else, well, you're going to remember the company thing. But this is the message I'd like you to remember, is we're going to have to reinvent around it again. And large-scale AI is HPC. If you go to AI conferences and you talk about what it takes to build large-scale AI, it's high-performance I/O, fast computing in the middle, and high-performance communication libraries. What do? That, right? We just happen to do it at double precision. If you take them apart, to make them scale, you have to look at parallelism at 3 levels: data parallelism, operator parallelism, pipeline parallelism. It's exactly what we do, right? They wouldn't have gotten there. All the big deep speed, GPT, they're all MPI based at this point. So, it is HPC. And last time, the commodity marketplace, we had nothing to give them. We just took stuff and built machines. Now we have lots to give them. One is sparsity, right? Unfortunately for us, sparsity means everything's on the diagonal of the matrix and everything else is zeros. In AI, sparsity is randomly distributed zeros throughout the matrix. We're gonna have to build all new sparsity algorithms, but who's best positioned to do that? Where is the background in numerical methods, right? It's not in the AI community, it's in the scientific community and sort of partial differential equation committee. So performance tuning is performance tuning, and we're gonna have to do it. So Torsten puts this best from ETH Zurich that AI is a gravity well. 64-bit performance is what it is. Nobody cares about making more. We're gonna have to figure out how to live with it. So also, if we do that well, we can improve the power it takes. And let me just stop right there, right? So we're gonna need AI for science, for our scientific users, and do the traditional stuff. We're going to need to take all we know about making systems big and give it to the AI community, at which point they might replace us by being ubiquitous. And we need to figure out how to use their hardware to do the science we want to do, because that's all the hardware we're going to get. So right now, AI still needs us because we're the only ones who know how to scale it up and make it go fast. But if we win, maybe the AI will give my talk next year. So thank you very much.